Okay, so you've seen some trends between pressure, volume, pressure and temperature, volume and moles. These topics were studied centuries ago by several different people, and their relationships, for the most part, have held true through time. Something to make note of. These laws work best for what is called an ideal gas, which technically doesn't exist. Okay? Ideal gases fit all assumptions necessary to make these equations work perfectly based on what's known as the kinetic molecular theory. Some of these components are true. Gases consist of tiny particles that are far apart relative to their size. That is true. Okay. One thing, collisions between gas particles and between particles on the walls of the container are elastic collisions, meaning they bounce off each other perfectly without losing any energy due to friction or anything like that. So no kinetic energy is lost in an elastic collision. Gases are in constant rapid motion, therefore they possess kinetic energy and the energy of motion. Okay, so if you think about it, as temperature changes, this can become more true or less true. There are no forces of attraction between the gas particles. If they are nonpolar, that is true. The average kinetic energy of gas particles depend on the temperature, not on the identity of the particle. There is a piece of kinetic energy that mass does relate to, but since we are dealing with things that are so tiny, for the most part, that's true too. So, real gases, on the other hand, generally don't fit all of those kinetic molecular theory components completely. First off, a lot of gases do attract each other. If you have a polar gas, they're going to be attracted to each other. Even if you have nonpolar gases, there's still going to be some very slight weak attractions among them. Real gases do have volume and size, okay? And then one of the key things is that the collisions are not elastic. So anytime a gas molecule bumps into something, either another molecule or a wall, it actually loses a little bit of its energy, transfers it into the whatever it's hitting. Okay? So, these laws work because there are situations where we come really close to the gas acting like an ideal gas. Okay? If we keep things at high temperature, okay, temperature relates to kinetic energy. The higher the temperature, the more kinetic energy something has, the closer we can get to the molecules actually acting like they keep all of their kinetic energy and they're constantly moving very quickly. Okay? Another thing is low pressure. Low pressure allows things to expand out more, have more space in between them. Okay? And then as far as the interactions go between the molecules, if we use very small non-polar gas molecules, the attractions among the molecules would be at their lowest. So these are the situations where we have gases that really closely fit ideal gas behavior. Okay, so like when we do a lab with hydrogen, if we do it at a very high temperature, a low pressure, and then hydrogen is a very tiny non-polar molecule, hydrogen can act like an ideal gas. Whereas the opposite of this, if we do things at a low temperature, if we do things at a high pressure, or you use a very large gas molecule or anything that's polar, then these laws don't hold as well. Okay? This is something to make note of. We are going to assume we're dealing with ideal gases in this classroom. Okay? But just keep this in mind. Especially if you ever go further into chemistry, you'll probably run into situations where you have to acknowledge the fact that we actually really don't work with ideal gases. So, first relationship was Boyle's law. Pressure is inversely proportional to volume when temperature is held constant. Okay, so that means as pressure goes up, volume comes down. Okay? And the multiplication factor of those two values stays the same. So if you decrease pressure, then volume is going to go up by a certain amount to maintain that relationship. So an inverse graph looks something like this. Okay? Sometimes, depending on how detailed the data is you get from a lab, you might see this relationship look more like a straight line. but it is a true inverse, so there should be a curve to the line. Okay? So, example of using Boyle's law, we have a balloon that has a volume of 340 milliliters at 1.5 atmospheres. What will the volume of the balloon be at standard pressure? Right? Now, here I'm writing in assume temperature is constant. You can make that assumption even if it's not written there. The only thing you see changing is volume and pressure, and then it's a Boyle's law problem. Okay, so here's my volume 1, here's my pressure 1, and then standard pressure is going to be pressure 2, and V2 is our question mark. So I have P1 V1 equals P2 V2. I'm going to plug in numbers. 1.5 ATM times 340 milliliters is equal to standard pressure in atmospheres. It's going to be 1 atmosphere. Okay, and that is an exact number times V2. So to solve for V2, we divide by 1 atmosphere, which really doesn't change our number any, and we get 540 milliliters. Okay, so for Boyle's law, your units do not matter as long as they are the same. Okay, your two pressures have to be the same kind of unit. Your two volumes have to be the same kind of unit. Okay, so if you get things that are in different units, then you need to convert them to the same one. So next relationship, Charles' law. So the volume of a gas is directly proportional to the temperature. Okay, and if we are able to reach that theoretical 0 Kelvin, the volume would actually drop to 0. Okay, so again, with Charles' law, we're assuming pressure is constant. Key to calculating anything where we have temperature in there, you have to put in kelvins. Reasoning for that, if you put in 0, okay, say for 0 degrees Celsius, down in the bottom there, that's undefined. We can't calculate that. So we have to use kelvins to allow us to actually deal with temperatures below 0 degrees Celsius. Okay? So, graph of Charles' law will look like a positive sloped linear line. Okay? Because as one increases, the other will increase by the same factor. So if you double one, the next one doubles. So, a gas at 45 degrees Celsius has a volume of 56.4 liters. What will the volume of the gas be if the temperature drops to 21 degrees Celsius? Assume pressure is constant. Okay, so here I have my T1, here I have my V1, and then I have T2, and V2 is my question. Okay, so the equation for Charles' law is going to be V1 over T1 equals V2 over T2. So I plug in my numbers. So I'm going to have 56.0 liters over, not 45, but I need to make that Kelvin. So I'm going to add 273, and that makes 318 Kelvin. And that's going to be equal to V2 over 21 degrees Celsius, but in Kelvin that would be 294 Kelvin. Okay, now to solve for V2, to get that alone, I'm going to multiply both sides by the 294 Kelvin. So those cancel, and V2 is going to be equal to 294 Kelvin times 56 liters over 318 Kelvin. Kelvins are going to cancel, which is why I still end up with liters as my units. And that gives me 51.773 and some odd numbers. So just to do some sig fig practice. So I had 3 sig figs and 56.0 liters. And it looks like I only have 2 sig figs with my temperatures, except you got to remember 45 plus 273, the last decimal they share, that really does mean 318. All 3 sig figs do count. Same thing for the 294K. So my answer here would be 51.8 liters. I do have 3 sig figs. Okay. So next law, Gay-Lussac's law. Pressure and temperature of a gas are directly related as well. Again, volume has to remain constant for this to hold true. And once again, you do need to remember temperature goes in kelvins. Okay? So if your starting pressure and temperature, when you divide them, make a certain number, no matter the changes that occur, they still have to divide out to that same number. So again, direct positive linear relationship. And an example of when we might use this says the pressure of a gas is 450 millimeters of mercury at 32 degrees Celsius. At what temperature will the gas have a pressure of 1.2 atm? Assume the volume is constant. So I have P1 and temperature 1, and then this is going to be my P2. So I have P1 over T1 equals P2 over T2, and I'm going to do 450 millimeters of mercury over 32 plus 273, which makes 305 Kelvin. Now, when I plug in my pressure for the next one, I have to make sure that they are in the same units. So I'm going to convert 1.2 atmospheres to millimeters of mercury. Okay, so 1 atmosphere, 760. That ends up becoming 912 millimeters of mercury. Since so far I have not switched from any sort of like addition and subtraction, I'm still going to be multiplying here. I'm not going to actually cut my sig figs yet. So I want to wait until the end around. And then T2 is my unknown. Okay, so when you run into this situation where you have something stuck on the bottom, cross multiply to get it out of there. So we're going to have 450 millimeters of mercury times T2 equals 305 Kelvin times 912 millimeters of mercury. Okay, then to get T2 by itself, I'm going to divide by 450 millimeters of mercury. Okay, so that cancels out the 450 millimeters of mercury, which means T2 is equal to 305 Kelvin times 912 millimeters of mercury divided by 450. So unit-wise, my millimeters of mercury will cancel out. So that means T2 is going to be equal to, I get 686.81 or so Kelvin. And then if I want to account for sig figs, I do have 3 in the 912. I have 3 in the 305, but 450 is only 2. So I'm going to make that 690 Kelvin. That's my final answer. Okay? Now, sometimes you can't control for one of the 3 variables. So everything's changing. Pressure, volume, temperature. So the true kind of like relationship between pressure, volume, and temperature is right here. Okay? And all of these, if you make something constant, like say you have volume being constant, okay, it becomes, your volumes can become 1s, and then you have P1 over T1 equals P2 over T2. So really, this equation tells you all of the relationships of the other 3 laws, Boyle, Charles, and Gay-Lussac. So this is the thing that I will give you on a test. P1 V1 over T1 equals P2 V2 over T2. Okay? If there's something that remains constant, like say volume, put a 1 in for it. Okay? Or remember that if volume's constant, then really all you have to worry about is P1 T1 and P2 T2. Okay? But a lot of times you do run into everything changing a little bit. So we have in a lab, 65.2 milliliters of a gas is collected at 22 degrees Celsius. The pressure of the dry gas was 689 millimeters of mercury. What would the volume of the gas be at STP? I want you to think carefully about this, because we've actually done this calculation in a lab before. And at that point in time, you didn't know the relationship between pressure, volume, and temperature. But now you do. So think about if now you understand why we did the calculation that we did. So, here is V1, here is T1, and P1. Okay? And then volume at STP, so that STP is going to give us our P2 and our T2. So V2 is going to be our question. So we have P1 V1 over T1 equals P2 V2 over T2. Okay. So I'm going to have 689 millimeters of mercury times 65.2 milliliters over 22 plus 273, so I'm in Kelvin. So that's going to be 295 K, and that's going to be equal to standard pressure is going to be 760 millimeters of mercury. Standard temperature is going to be 273 K, and then I'm running out of space to write that in there, but that's all multiplied by V2. Okay, so that means V2, to get that by itself, I'm going to have to multiply by standard temperature and divide by standard pressure. So I'm going to end up with, rewrite this just a little bit, I have my volume, okay, times standard temperature over my 295K times my starting pressure over standard pressure. Lo and behold, this is set up the same way we did it in the lab. And that's going to be equal to V2. Okay? So, calculate this out. I get 54.70008. So, I have 3 sig figs in all of my numbers. So, I get 54.7 milliliters. Alright. And the last relationship, we've actually already talked about this one, but it is named Avogadro's law, and that's that the volume of a gas is directly proportional to the amount of particles in the gas. Okay, and that's our relationship that a mole of gas, specifically at STP, will be 22.4 liters. Okay, reason why 22.4 liters only works at STP is because if we change temperature, volume changes. Okay, so this, or if we change pressure, volume changes. So when using the 22.4 liters, you do need to make sure that you have done something like the problem before and ensured that your volume was done at STP or adjusted for having occurred at STP. So make sure you do the online assignment and see you in class.